Hello everybody, I'm Brian Litz. I'm here to talk to you today about ballistic calibration in the AB Quantum app. Okay, so you've got your long range rifle, you've gone to the range, you got your 100-yard zero, you've got your loads, and now you're out shooting long range. Okay, you've got a fire solution and you shoot at your long range target, and lo and behold, you've got some error. Okay, so what do you do about that error? That's the topic of this video. There are several ways to calibrate your ballistic solution if you do find that you have error at long range, and that's what we're going to go over. We're going to go over how to do that the very first time you go to the range, follow-up calibrations, if you have multiple corrections to make, and also we're going to cover ballistic calibration for subsonic muzzle velocity like 22 rimfire, 300 blackout, air rifle, things like that. All right, so let's get started. The most common way that you're going to encounter this is with this, standard long-range rifle with supersonic muzzle velocity. Now, the first thing you have to do is pick what the range is that you're going to calibrate at. Okay, you don't want to try and do this with a target that's too close or too far. You want to target in the transonic range to calibrate at. Okay, what do I mean by transonic range? That's the distance that your bullet slows to transonic velocity. Okay. Bullets are going to start out between 2 and 3 times the speed of sound, and when they slow down to the speed of sound, that's what we call transonic range. Now, if you calibrate too close, okay, the problem there is that you don't have very good resolution. Okay, if you try to calibrate at 200 or 300 yards or even 400 yards, you don't have enough drop in relation to your group size to really resolve what your actual drop is. There's just not enough of it yet. So you would do a poor job calibrating at a range that's too short for that reason. And then you don't want to calibrate at too far of a range, because if you calibrate at a range where your bullet is in the transonic zone, it's common for bullets to have stability issues there, and flight gets a little bit erratic in the transonic zone. So in order to have that messiness out of your calibration, you'd want to calibrate at a distance inside that problem area. So we call that the transonic range. It begins at about Mach 1.2. Okay, that's about 1,340 feet per second. All right, and what we're showing here in these Mach CD plots, all right, every one of these black lines is the track for one shot. Okay, these are 10-shot groups. And you'll see that all those lines are together from the muzzle out to transonic range. Somewhere around Mach 1.2 is where we start to see the drag stratify. All right, that's because of the stability challenges that you have at transonic with spin stabilized bullets. All right, but what we see is a very clean and repeatable track of the drag from the muzzle out to that range. And so that's why we don't want to calibrate any further, because we start to get into that unknown, poor stability range. All right, so what we've established so far is that to calibrate a long-range rifle with supersonic muzzle velocity, you want to calibrate at transonic range, and it's going to be between 8 and 1,200 meters typically for most things. Okay, the AB Quantum app will show you the distance that corresponds to transonic range, and I'll bring up that example right here. So you can see that we've got the DSF pulled up for CDF and MV truing. It's going to give you a range. Here it's telling you between 932 and 1027. That's the range that you want to calibrate muzzle velocity or CDF at. Okay, that's telling you what the transonic range is. So that's step one down. We've identified what transonic range is. We know what distance we're going to do our calibration and why. Okay, now we have another question. Are we going to calibrate muzzle velocity or CDF, the custom drag factor? Okay, so there's two likely ways that your trajectory has error at long range. One of them is that you're modeling a muzzle velocity that's not accurate. It's also possible that you're modeling, there's some error in the drag that you're modeling for your projectile too. Until recently, muzzle velocity was the only option we had for calibration, and then Garmin came out with those amazing radar chronographs, also the lab radar chronograph. If you have a radar chronograph measuring muzzle velocity while you're shooting long range, that sort of takes that variable out of the equation, and any error that you would have is likely in your drag model at that point. So that would be the purpose of the CDF calibration. Okay, so that's kind of how you know which one you want to do. If you don't have a chronograph and you're shooting long range, odds are there's more error in your muzzle velocity than there is in the drag model of the bullet. So if you don't have a chronograph, you want a true MV. If you do have a chronograph, I mean, not just have one, but you're using it in the string of long range fire that you're calibrating with so that you know your muzzle velocity, In that case, you would calibrate the drag of the bullet with the CDF. Okay, I'm going to dwell for a little bit here on this difference between muzzle velocity and CDF calibration, since it is a really common question and it's kind of a sticking point because it requires you to know something about your uncertainties to make the right choice here. All right, so here's an example analysis. It's a 6.5 Creedmoor with a 140 hybrid at 2,800 feet per second. All right, and in this case, the transonic range, we hit Mach 1.2 at 1,000 meters. Okay, so what we're looking at in this graph, we have the blue line that represents the original trajectory, and then we're saying that we're seeing a 0.5 mil of error at 1,000 yards. Okay, the original trajectory had us at 9.7 mils of drop, and we actually hit 0.5 mil low, we're saying. So we hit with 10.2 mils of drop. All right, now there's two choices. We can either calibrate that 0.5 mil of error at 1,000 meters. We can either calibrate that out with muzzle velocity cal or with CDF cal. All right, and we're going to look at examples of doing it each way. Okay, in the first place, if we do an MV cal, first I just want to show you what that does to your trajectory everywhere else. Okay, so if here's at 1,000 meters, we did an MV cal to correct the trajectory by 0.5 mil. That's what we're seeing. This is how much it changes your trajectory beyond 1,000 meters. Out to 2,000 meters, you're looking at 1.8 mils of difference that results from the 0.5 mil that you trued at 1,000 meters. All right, does that make sense? So the next one, if we look at, instead of muzzle velocity cal, if we did a CDF cal at 1,000 to correct that 0.5 mil of error that we saw, you see it's still perfect at 1,000, but then look how much more error you have in your solution at these further ranges. It moves your trajectory by 3.6 mils at 2,000 yards versus just 1.8 mils that the muzzle velocity correction did. So this is just something to be aware of what it does to your trajectory. The CDF is far more consequential and is far less likely to be the thing that's actually in error if you're using bullet models from the AB library. Okay, and then this last one is showing you the error between. So if you really had a muzzle velocity error, but you accidentally or mistakenly used the CDF calibration, this is showing you the error that you would have in your trajectory. So between the muzzle, or between your zero range and your calibration range, the error is always going to be minimal, right? Like you only have one click of error through that range. But beyond the range that you calibrated, okay, that's going to be perfect because that's where you pinned it at. You told it where you hit there. But beyond that range, because if you calibrate the wrong thing, you're misrepresenting your trajectory. It's only going to be right at the one distance, and it's going to be wrong everywhere else. And this is how wrong it will be. This is how the error would propagate beyond the range that you trued at or calibrated at. Okay, so you can see at 1,500 meters, you've got a 0.7 mil error, and then at 2,000, you've got a 1.7 mil error. Okay, that's in the event that you chose the wrong thing to calibrate. I want to show you in quantum what it looks like whenever you're calibrating one or the other. So here's our situation. We have our 9.7 predicted mils of drop at 1,000, and our muzzle velocity, that's based on a 2,800 foot per second muzzle velocity. Now, if we tell it we hit at 10.2 mils, it's calculating a 2,739 foot per second muzzle velocity instead of 2,800. And if we say apply that muzzle velocity and confirm it, now you see our elevation change to the 10.2 that we saw as reality, and it's now modeling our muzzle velocity a bit slower. That's like 61 feet per second slower in order to make up for that 0.5 mil of error we told it we had at 1,000 meters. Okay, now you can also see if you go back into your profile, you'll see that your muzzle velocity was changed there. Okay, there's the 2739. All right, I'm going to put that back to 2800, and we're going to go back out into the HUD, and we're back to 9.7. All right, now if we wanted to calibrate with CDF instead of muzzle velocity, it's the same process. We just select CDF, we're at 1,000 meters, and we're seeing 10.2 mils of drop. Now in this case, it's showing us the calculated CDF, the calculated custom drag factor is 1.078. So that's telling us that in order to account for this 0.5 mil of error we saw at 1,000 meters, we'd need to adjust the drag by 7.8%, nearly 8%. Okay, I'll tell you, to put that in perspective, that's a lot of drag adjustment, okay? If you're using a bullet from the AB library, chances are it's within 1% of your actual drag, okay? You could be up to 2%, plus or minus 2% from it, but you're rarely going to be more than 3% error in drag. It's possible, but not likely. You know, if you trim or point your bullets, you might need to use more than a 3% correction. But if you're using unaltered bullets, you really shouldn't be needing very much of a custom drag factor. All right, in this case, it's showing 7.8%. It's most likely that that trajectory would be corrected with a muzzle velocity adjustment rather than a drag adjustment. Okay, but it works the same way in the app. We select CDF 10.2. It tells us the calculated factor. We apply it, and our dope is corrected 1,000 now. Now, what it does to our dope beyond that, I've showed already in the other slides. We understand the range that we want to calibrate at, and we understand how to choose between muzzle velocity or CDF calibration, depending on our circumstances. Now, suppose you want to do some follow-up calibration. That can mean two things. Either you're shooting at further ranges now, so you've calibrated at 1,000 and you want to calibrate at further distances. Maybe you've got some remaining error out there. Or follow-up could mean you've trued to transonic last month and now you're out shooting again and you're seeing error and you want to calibrate that out. How would you do a follow-up calibration to one you've already done? Okay, so now we're getting into a little bit of the more complex considerations for ballistic calibration. All right, so if you're recalibrating after you've already done it at that distance, more than likely you're going to want to do the muzzle velocity calibration. Why? Because muzzle velocity actually does change a lot when you go to the range. It changes in response to temperature, to barrel fouling. The humidity of the powder in your rounds affects your muzzle velocity. So a lot of things affect it, and so it can be different every time you go to the range. So it's very reasonable to do MV cal, you know, as follow-up calibration to something you already have, because it's likely your muzzle velocity really did change. Now that's different than the CDF, right? Once you have a lot of bullets from a certain barrel, the actual drag of those bullets is not going to change on subsequent shooting trips. You know, if you had a BC or a CDM value one day, that isn't going to change with atmospherics. Atmospherics have their different effect, but the BC or CDM, it's going to be the same for those bullets out of that barrel. So you don't want to be changing the CDF every time you go out and shoot. The recommended thing to do is to go out shooting at least once with a good radar chronograph, establish your muzzle velocity, and do the calibration on the CDF, okay? Get your CDF established in a very careful session of range calibration, and then that will be fixed. And then after that, you don't even really need the chronograph because you can do an MV cal and establish what your muzzle velocity is based on knowing what your drag is, because you've already established that when you had a chronograph. So that's what I would recommend. If you have a chronograph, use it at least once to establish your drag, and then after you have your drag established, leave it alone and calibrate your muzzle velocity every time you go to the range if you have to, because it really could be different. So that takes care of the follow-up in the sense that you're redoing a supersonic calibration. All right, now we'll talk about the other follow-up calibration, which is you want to do it at further ranges. All right, think about it. You can't redo your MV cal to be on at 1500 as a different muzzle velocity than what it was at 1000. Same with the custom drag factor. That doesn't, you know, it doesn't have jumps and changes as you go out in range. It's one scale factor that's going to apply to your whole drag curve. All right, so if you are perfect at 1000 and you see error at 1500, for example, what you're going to want to calibrate in that case is the DSF, or the drop scale factor. Okay, the drop scale factor behaves different than the first two. Drop scale factor will begin applying its effect at transonic. It's really for the long range side of calibration. So it'll begin applying at Mach 1.2, and it will build to whatever the first point you have in the DSF table. All right, so in this example, we calibrated muzzle velocity at 1,000 meters, and now we're going to calibrate DSF at 1,500. All right, and you can see what that does. You can calibrate at 1,500 and you can calibrate again at 2,000. And the DSF is basically pinning your drop to what you say it is at that Mach number, not necessarily that range, okay, at that Mach number. And then it's going to interpolate between those points that you tell it you hit and basically just connect the dots along your trajectory to what you're training it with the DSF calibration, okay? DSF, another thing to know about that is linear with Mach, but it's not linear with range. All right, the idea of what DSF is trying to do, what it normally is accounting for is, think about it, you're shooting beyond transonic range by the time you're doing a DSF calibration. So beyond transonic range, you've got so much drop that you probably have either a prism or a periscope or an adjustable scope base, something to account for all of the drop that's beyond the range of your scope's internal adjustment. Okay, and whenever you start augmenting your elevation correction with things outside the scope's internal adjustment, there's a good chance you're going to introduce some error from that. Okay, they're usually not perfect adjustments. And the DSF, that's one thing that it's going to account for, is the actual amount that your sight adjustment is moving in relation to those devices. Okay, and it's easy because you can just tell it what drop you had at what range and at numerous points, and it'll connect those dots and keep you in line with that trajectory whenever you come out and shoot again. Okay, so that's the two methods of follow-up, either redoing supersonic or extending your calibration beyond supersonic into the trans and subsonic with DSF. I'll show you the example of how to do the DSF calibration in the quantum map. So we come in here and you see it's got our calibration from 1,000, where we told it at 1,000 meters, we hit at 10.2, and it gave us that correction for the CDF that we have applied. All right, so now we're going to come into DSF and we're going to give it our next range. Say we're going to do a DSF calibration at 1,500. All right, and it's telling us our drop there is 23.7, but suppose we hit a mil low. Okay, suppose we hit with 24.7 mils of drop. And so in that case, it's telling us the calculated DSF is 1.044. And we're going to say, all right, use that DSF. And now you can see how it corrected our trajectory to 24.7 mils. Now we can do that again if we wanted. If we want to come into 2,000 meters, and it's calling for 46.4 mils, but suppose instead of more drop, this time we had less drop. Suppose we hit at 2,000 with 45.4. Okay, so we come in here, 45.4. That's telling us our Mach number and our calculated DSF at that range. And if we use that, then it immediately corrects our predicted elevation to be 45.4, just like we said it was. And so you can do this with several DSF points. It'll connect the dots in your trajectory and make sure that you don't have any error based on what you saw when you actually shot there. Okay, there's one more thing we're going to touch on, and that's going to be truing or calibrating for subsonic muzzle velocity. All right, so things like 300 blackout, 22 rimfire, air rifle, anything with muzzle velocities, 1,100 feet per second or less. So in this case, it's different from the supersonic truing in several ways. First of all, you're starting out below transonic, so immediately DSF can apply. All right, so that's something that you have available for subsonic truing that it's not available in the same way for supersonic, is that DSF can be your one and only truing for subsonic if you want it to be. Now, when you consider, muzzle velocity or CDF cal, one of those is almost useless in subsonic, and that's CDF cal. That's because the drag that's applied at subsonic speed is so low that it has such a small effect in relation to muzzle velocity that it's not going to affect your trajectory very much at all. That's what's being shown in these charts here. So we've plotted a baseline trajectory out to 500 yards for subsonic, and we're showing the effect of a plus 50 foot per second and a plus or minus 10% drag. All right, whenever we do minus 10% drag, it's almost the exact same trajectory. I think it's within 0.3 mils at 500 meters with a 10% change in drag. But when we have a 50 foot per second change in velocity, the change is very huge and dramatic. Okay, that's shown in this other plot. It's just showing you the difference where changing drag by 10%, yeah, it gives you a 0.3 mil difference. Changing muzzle velocity by 50 feet per second gives you almost 2 mils of difference. So all of that to say that if you're shooting something with subsonic muzzle velocity, you really want to look at muzzle velocity calibration or DSF truing. The CDF isn't going to do much for you with subs. And so I'd give the same advice is if you have a good chronograph that you're using during the calibration, then you know your muzzle velocity, so use the DSF cal to calibrate out your error. If you don't have a chronograph when you're doing your calibration, then you could use the MV cal or the DSF cal. I would probably use MV cal. All right, so that's ballistic calibration in a nutshell. So the first caveat is going to be that you've done your 100-yard work. Okay, you've got a good 100-yard zero or 100-meter zero, and you've verified your scope tracking with a tall target. There's other videos that you can watch that break down in detail how to do a tall target test. So that's the first caveat. Make sure that you've done the work at 100 yards to have your sight system calibrated. And the other caveat on this is to really consider it, think of it as a calibration exercise. That's really what it is, right? You have to account for Coriolis effect on your vertical. You have to account for the head or tailwind component of the wind, right? So you got to put in the actual wind speed and direction. Do your level best to put in every detail as carefully as you can so that the ballistic solver arrives at the correct custom drag factor or the correct muzzle velocity so that it's accurate in the future. If you have error when you do your calibration, then that error gets baked into your solution. So all your future shooting is going to have that error baked into it unless you do a really clean, good calibration. Okay, so those are the two caveats. Do your 100-yard work and treat this like a calibration exercise. And if you keep those things in mind as you're selecting your calibration practices and going through, then it's going to work out for you. You'll be able to clean up that little bit of error that you saw when you first went out and shot, and basically train your ballistic solver to match your actual equipment in a way that's repeatable every time you go back to the range, right? If you do a poor job at calibration, then it'll be new every time you go there because you're not doing it right. But if you do it right, then every time you go to the range, that is going to be, the ballistic solver will be modeling your equipment correctly, and you can count on being on target with the first shot. Thanks for watching. If you want to see more of our instructional videos, check out the link in the description.